Okay, so welcome to lesson 7. In lesson 6 we saw that we could use the experiment and determine the molecular mass. Now that method that we saw is straightforward, but sometimes we can be told to draw graphs from the experiments you get using that, from the values you get using that experiment. So someone could tell you to draw graphs. So several graphs can be determined or can be obtained from values that you get from that experiment. Because what did we see that we get from that experiment? From that experiment we saw that we actually get the mass of the solute, we get the mass of the solvent, we get the freezing point of the solute and freezing point of the solution. So someone could actually tell you to vary the freezing point, to vary the mass of the solute. You keep on adding different masses of the solute to a given amount of the solvent. So meaning that you will carry out more than one experiment, you get many values, and those values can be used to plot a graph. So I'm going to say that several graphs can be obtained from experimental values, from experimental values using the cryoscopic method. Okay, so what would happen here is that we would get a fixed mass of a solvent and then keep varying the mass of the solute added there, so that we get several freezing points. And when we get several freezing points, then we could actually look at very many, around 2 graphs here. So let's look at the theory first. We said that dt, we want to look at this, that a colligative property depends directly on the number of moles of a solute added, but not the nature. So if this n is number of moles, we know that, we can say but n is mass over molecular mass. Okay, so someone could as well say that dt is directly proportional to mass, but inversely proportional to molecular mass. Now, if we remove the proportionality sign for the cryoscopic method, then the constant should be the cryoscopic constant, Kf times mass over molecular mass. Now, in our experiments, we don't get dt, but we get the freezing point of the solutions varying. So if I keep varying mass of the solute, when the mass of the solvent is fixed, I'll keep getting different freezing points of the solution. So if I substitute the formula for getting dt we said is a freezing point of the solvent subtract freezing point of the solution. So you will get T naught minus T. This is the freezing point of the solution. This is the freezing point of the solvent. Should be equal to Kf times mass over molecular mass. We can put whatever is a constant here. Of course, molecular mass of the solute is constant. Kf is a constant. And then we would have something like T naught minus T is equal to Kf over molecular mass times m. These ones are constant, m is a variable. M is the mass of the solute being added. Now, What is a constant this side? This side, the freezing point of the solvent is a constant, doesn't change. But the freezing point of the solution will keep changing depending on the mass that has been added. So the variables are freezing point of the solution and freezing point and the mass of the solute added. So I could make this the subject, this variable here, freezing point of the solution. If I make it the subject, then I'll have T being equal to Kf, which is minus over molecular mass times our variable m plus T naught. So this is the equation that we can base on to plot a graph. Remember this one here, this one is now freezing. So I can say that where T is freezing point of the solution. So that one will keep varying. M is mass of the solute that you will keep adding in the same amount of the solvent. And then T naught is freezing point of the solvent. That one doesn't change. And then we have Kf as the cryoscopic constant. Cryoscopic constant. And Mr is molecular mass. And if that is molecular mass, so we could plot a graph of the freezing point. We can plot a graph of freezing point against mass of the solute added. So you could have freezing point is in degrees Celsius over mass against mass of solute added. Mass of the solute could be grams per 1,000 grams of the solute, of the solvent. We can fix the solvent there. And then when you look at the equation that we have generated here, and relate it to equation of a straight line, it could give you the shape of the graph that we intend to grow. Let us try to relate. Relate with the equation of a straight line. We know the general equation. Relate with the general equation of a straight line. Y is equal to mx plus c. Okay? Y is equal to mx plus c, where m is the gradient. So we could now see that if I brought in my t is the y-axis, this one should be equal to negative Kf over molecular mass. My gradient is Kf over molecular mass times m. M, the mass, is the variable on the x-axis, this one here. And then plus T naught, which is the intercept on the y-axis. However, what we note is that this one has a negative gradient and this one has a positive gradient. So our graph is a straight line with a negative slope. And that would look like, would have, if we plotted, would have a straight line like that. And there is an intercept. This intercept is the freezing point of the pure solvent. And then if you go ahead and obtain the slope, if you obtain the slope, or what you call the gradient, then the gradient should be equal to what we see here, matching with the gradient. The gradient should equal to negative Kf over molecular mass. Meaning that there are quite many things that you would ask the examiner. For example, a practical is set to you, you carry out, this can be set in paper 3, you carry out the experiment and they tell you, you keep varying the mass. For example, you start with 1 gram, 2 grams. This is the mass of the non-volatile solute. And then the mass of the solvent is constant. So when you keep varying, they can tell you, use your graph to determine the freezing point of the solvent. Freezing point of the solvent is the intercept you get, the y-axis. So that means when you're plotting this graph, this one, the numbering of this should begin from 0, because the y-intercept is a value on y when x is 0. So this one should begin with 0 going the other side. And then the other thing they can ask you is to determine either the cryoscopic constant or molecular mass, depending on what they have given. If the question has given the molecular mass of the non-volatile solute, they can ask you to determine the cryoscopic constant. But if they have given cryoscopic constant, then they can ask you to get molecular mass. All of them will come from the fact that slope is equal to Kf negative over molecular mass. So any of the two here could be used to determine whatever will be missing, because on your graph you will always be able to determine slope. So molecular mass could be simple as that, as the first one we looked at in lesson 6, but could as well go to graphical values. Another graph that we could actually develop here, apart from this one, someone could simply tell you to plot depression in freezing point against mass being added. What if from this graph that we had, that dt is equal to Kf over molecular mass times mass? Someone could just tell you to plot a graph of depression in freezing point degrees Celsius, depression in freezing point against mass added in grams per 1,000 grams of the solvent, okay, of the solvent. So when you look at this graph and you compare this equation here that we had, and you compare it, this is what we had before we substituted in the dt. If you compare this with the general equation, we could still come up with another graph. This one is our variable on the y-axis, depression in freezing point. Mass is the variable on the x-axis, mass added here. And then the gradient this time is positive, Kf over molecular mass. But then what we see that there is no intercept. Or intercept is 0. There is intercept, but the intercept is 0. So this time we have a positive slope. So you will have a graph going through the origin and its slope that you will be able to determine. Slope should equal to Kf over molecular mass. So there are two graphs here that we can develop from the values that we obtain using the other experiment. And still you can say that you can determine molecular mass using this, or you can determine molecular mass using this. The only difference, the other one is negative, this one is positive. Here we are plotting the depression. the difference in freezing point of the solvent and freezing point of the solution. That means that if they are to ask you about this, then the freezing point of the solvent should be known. So that in the experiment you get the freezing point of the solute, and then you simply keep subtracting and you get the depressions, and then you plot a graph, and you will be able to get the molecular mass or the Kf. So this is all about the experimental determinations, the experimental determination of molecular mass using the cryoscopic method. We saw you could simply do one experiment, get the values and compute. However, sometimes one value may not be reliable. So we can expand it for purposes of paper 3, and then they look at the graph work. We can do graph work of plotting either freezing point of the solution versus mass being added, or we can have freezing point, depression of freezing point against mass being added. Some of the tips when you are drawing these graphs is that one, a good graph should cover at least 3/4. A good graph should cover at least 3/4. Cover 3/4 of graph paper. Okay, should cover 3/4 of graph paper. Then you need to label the axes very well with units. If you don't label with units, then you won't really get the marks for this labeling. Then we should have a title. Let's use a good scale. So you state the scale you are using, and when you are drawing, you draw the line of best fit. Draw a line of best fit, because these are experimental values. They may not lie on the same line, but we can draw a line of best fit. So when we are marking, we look at your graph. How is it covering? We look at the labeling, the title, and then the scale you're using. But also you need to plot accurately because of the scale that you're using. You need to be able to tell, to plot very well using your scale that you have chosen. Otherwise, if you don't go with this, then graphs may not be correct. So if you want a good graph and get marks out of it, follow this. You go get a good scale that covers most of it. There are quite many examples in our UACE question banks. You can look at this. Practically, you get values and plot. Otherwise, this marks the end of the experimental determinations of molecular mass and other stuff using the cryoscopic constant method. When we come for lesson 8, we shall be looking at something else. See you there.